Eisenman, who's a professor of climate, atmospheric sciences, and physical oceanography at the Scripps Institution of Oceanography at UC San Diego. So you're probably wondering, what's the Dean of Physical Sciences up here talking about someone from SIO? Well, in the beautiful collaborative nature that is UC San Diego, we don't have any geologists or oceanographers or in the School of Physical Sciences. So I reached out to my friends at the Scripps Institution and found Ian, who is actually the perfect person to host Professor Hoffman. Ian got his BA in Philosophy and Physics from Williams College in Massachusetts, which does two things. First of all, I always knew physics and philosophy were the same thing. And this kind of proves it. So thank you, Ian, for that. And I know Williams well because I went to Middlebury. And those purple cows were our nemesis for many years, if you can call it football, but that we played. Ian then went and received a master's degree in physics from UC Santa Barbara and another master's degree from Harvard in applied math, so he keeps going back across the country. Then he earned his PhD in Earth and Planetary Sciences from Harvard, then was a postdoc fellow jointly at Caltech and University of Washington. Before starting here, his career here as an assistant professor in 2012, rising very quickly through the ranks, where he became a full professor in 2021. So Ian will be serving as the host for Professor Paul Hoffman, this year's Kyoto Prize laureate in the basic sciences in the field of Earth and Planetary Sciences. As Ian, I'm sure, will discuss, Professor Hoffman is widely known for his research on Snowball Earth glaciation, and particularly through his research in sedimentary rocks in Namibia. Ian was actually the perfect choice to serve in this host role, as his interests include paleoclimate research. In fact, he's published several papers himself on Snowball Earth glaciation. In addition to studying paleoclimate, Ian's group also studies the ocean and climate dynamics, including sea ice, climate feedbacks, large-scale circulations of the Earth, the ocean and atmosphere, as well as icebergs. So please join me in welcoming Professor Ian Eisenman to talk about the impact of Professor Hoffman's work.
All right, hello. Hello. It's a pleasure to introduce Paul Hoffman. He's one of the 2024 Kyoto laureates. Let me see if I can make this work. Excellent. Okay, so I'm going to start off by saying a little bit about Paul Hoffman's life and career. He was born in Toronto, Canada, 83 years ago. He's a Canadian citizen, and that's a big part of Paul's identity. He got his bachelor's degree right near Toronto at McMaster University in geology. And then he came to the US, to Maryland, and got his PhD in geology from Johns Hopkins University in 1970. And he spent most of the next couple decades or so working for the Canadian Geological Survey. And during this time, his research focused on plate tectonics. I'll say a bit more about that later on. He also spent some time at University of Victoria on the west coast of Canada in British Columbia. And then he was recruited to Harvard University as a full professor in 1994 and spent a decade and a half there from 94 to 2008. And on a personal note, during that time, I was at Harvard getting my PhD and master's between 2002 and 2008. And although I wasn't in the same field as Paul Hoffman, I work in physical climate science and he's a field geologist. We were in the same department and I got to know him quite well during that time. I think a real defining characteristic of Paul's personality is that he seems totally blind to hierarchy. And Harvard's a pretty hierarchical place, so he stood out in this regard. He treats everyone just the same, whether you're the custodian, a grad student, one of his colleagues in the department, or probably a Kyoto Prize laureate. And this carried with it a modesty and a real personal charm. He was really well loved by the graduate students. And I'm thrilled to be involved now in him getting this award. He retired from Harvard. He left around the time I did. And he's now an emeritus, he's an adjunct. I wrote adjunct. Yes, okay, he's an adjunct professor at University of Victoria, again on the west coast of Canada. And aside from science, he is a really, really avid long-distance runner. Always has been. I think the Boston Marathon is arguably the premier marathon in the United States of America. Paul's run the Boston Marathon many times, and once in his youth he placed in the top 10 in the Boston Marathon, which is a really remarkable feat. But that's not why he's getting this award. He's getting this for his science, so I'll say a bit about that. Let's see. Okay, so Paul is most known for Snowball Earth events, and I want to show a few slides here just to place those Snowball Earth events that Paul's known for, these hypothesized events in Earth history, in context. And so what I want to start with is just a picture of the global mean temperature on the Earth, averaged over every year in the instrumental record. So in San Diego, the annual mean temperature is something like 65 degrees Fahrenheit, it's a little warmer than that today. If you go a little up the coast in San Francisco, it's more like 57 degrees Fahrenheit, and San Francisco's in mid-latitude. The average temperature over the year in San Francisco is about the same as it would be if you averaged over the whole Earth, about 57 degrees. And so, and so you can see there's certainly been, this won't be a surprise to anyone, the globe is warmed from a temperature of something like 57 degrees up to like 59 degrees. To broaden these axes out a little bit, next I want to look at future projections of what the global mean temperature might do during the coming century. And I've shown that here. This is based on computer simulations of the future of the climate system that were developed in modeling centers all over the world and run very tediously on massive supercomputers all over the world. And the three different colors here are three different societal pathways. People talk a whole lot about this. Are we going to focus a lot on sustainable development, alternative energy sources, or have a fossil fuel driven economy? That's the different, that's the different colors, and then the spread, the shading around each color is just the uncertainty in this, the error bar due to, on the one hand, the natural ebb and flow variability of the climate system, and on the other hand, uncertainty in model in the physics of the climate system. So a whole lot of discussion about this, which line are we going to end up on? But we can expand these axes out a bit more, thinking about what the Earth looked like 20,000 years ago, during the height of the last glacial period. And at that time, there was a massive ice sheet that covered pretty much all of Canada and a good bit of the northern states of the northern US. And the temperature was a good bit colder, and it kind of, okay, somewhat dramatically colder compared to what we're talking about now, some 20,000 years ago. Okay, so now I'm going to put Snowball Earth events on this plot. And there they are. This is so exotic. This is such a remarkably different planet than we live on today. So this is, the idea of Snowball Earth events, episodes, is that some hundreds of millions of years ago, say 600, 700 million years ago, the Earth may have once and perhaps multiple times gotten so cold that the globally average temperature of the Earth was colder than -70 Fahrenheit, which is probably colder than most people in this room have actually ever experienced. That's very, very, very cold. What would an Earth like that look like? So, see here. This is a rendition of what it might look like. So here's the modern Earth with a big pile of snow in Greenland. Another one we can't see in Antarctica, but not much elsewhere. This is what a Snowball Earth might have looked like with a climate that cold. Just thick ice covering the entire planet. Perhaps not the entire planet, perhaps just most of it. There's a lot of debate about this, but a very, very cold planet. This is the idea of a Snowball Earth. I'll say a little bit about the history of the Snowball Earth. So, some 30 years or so ago, around the 1990s, evidence started to emerge that there may have been glaciers in the tropics a long, long time ago, 600 or 700 million years ago. And for context, by the way, modern humans that looked like us have been around for probably like a couple 100,000 years, so this is a long time earlier. But still at a time when there was life on Earth. So the idea was, evidence started to emerge that there might have been glaciers in the tropics at that time, and a hypothesis was proposed called the Snowball Earth hypothesis, and the idea was that the Earth might have been fully covered with ice. People, This sounds a little bit like the last introduction. People didn't take the idea that seriously at first. If we got into a snowball that looked like that, one question is how would we ever get out of it? The Earth's white, it's reflecting a lot of sunlight, it would just stay cold, and it seemed kind of impossible to get out. And it was just so different than anything we talk about for climate today, or even in the past tens of thousands of years, even in the period when humans walked on the Earth. It's so different, it was seen as so bizarre that it must be unrealistic that the Earth could have been so different than it is today. So it didn't receive a lot of attention, and Paul Hoffman got really interested in this and did extensive field work to study this, mostly in Namibia, Africa, and this was approximately during the time that he was at Harvard, around 93 to 2008, plus or minus. Paul Hoffman is very much a field geologist, and Paul likes to talk about field geology and how it involves the mind and the body and demanding a lot from both. So he would walk long, long distances in Namibia on foot to find important places where there's important geological structures, and then in real time look at those geological structures, try and interpret what they mean, form hypotheses in real time as he's out there, having been up for really long hours, walking really long distances. Probably easy for him as a marathon runner, but still pushing his limits, trying to form hypotheses and ask, what can I do to test those hypotheses, figuring out what samples to bring back, hammering these rocks, samples off of the formations, carrying them back to his base station, flying them back to the lab and analyzing them. To Paul, this was really an example of science in its purest form, requiring everything from the human body, the mind and the physical, and creating hypotheses and testing them. He did a lot of work like this, so Paul's very, very good at this, and he did a lot of work in Namibia, bringing home rocks, glacial deposits from the Snowball Earth period, and doing isotopic analyses of those in the lab. And ultimately what this led to was work that made a clearer picture of the Snowball Earth environment, but also a way more convincing picture of the Snowball Earth environment than had ever been created previously, and also giving evidence of how the Earth transitioned out of the Snowball Earth environment. And I think Paul made this, he's the name we most associate with the Snowball Earth events. He's really what put this on the map and made this such a popular and widely discussed concept. And the work also has implications for the evolution of life, and how life would have survived through the snowball and how it would have flourished as we came out, and importantly, the first multicellular animals evolved shortly after the end of the last Snowball Earth period, or the last proposed Snowball Earth period. So his work led to a dramatic increase in interest in Snowball Earth events. Okay, another topic that Paul worked on for kind of the first half of his career, a big period earlier in his career, is plate tectonics in Earth's early history. This is work that he did mostly when he was working at the Geological Survey of Canada in the 80s and 90s. So plate tectonics, we've all heard of it, living in California. It has to do with earthquakes. It describes the motions of the plates of the Earth that cause continents to form. Until around 1980, tectonic plate motions could only be traced back to about 500 million years ago. And by context, the Earth is some 4.6 billion years old. And so in the 1980s and 90s, while he was working at the Canadian Geological Survey, Paul carried out really extensive and careful geological field work in the Canadian Arctic. And the work he did demonstrated that the present North American continent formed around 2 billion years ago, and he traced plate tectonic activity back 2.5 billion years, which for the first time demonstrated that plate tectonics dates back to the first half of the 4.6 billion year history of the planet Earth. Okay, so that's the introductory stuff I want to say about Paul, and now I want to let him say a little bit himself and show a video of him giving a presentation. This is a video. This is a video of Paul presenting in 2018 to undergraduates, to students at a college in Canada. He's a really charismatic storyteller. People love going to his talks. I've seen him speak many times. And this is a clip from the end of the talk that he gave there about Snowball Earth and life evolution of life and how it was impacted by Snowball Earth.
So it looks like to me, I mean, it's just a story, but you're trying to think about ways of testing this with biomarkers about the cyanobacteria, as we've done here with the sterins for eukaryotes, that both cyanobacterial primary production in the modern ocean and also the dominant eukaryotic primary producers actually radiated and stemmed from the Snowball Earth events. So far from inhibiting biology, it actually was an important guide to the organisms we have in the modern world and the important insights as to what happened, and not from fossils, although this is a fossil, but rather from study of the molecular makeup of modern organisms. Okay? So I'd like to think that the modern organism contained a legacy of these Snowball Earth events. And the final slide, I think we need a new model for Snowball Earth that includes cryoconite and cyanobacteria living in cryoconite pans. So I suggest that we might use this one. And finally, I'd like to acknowledge my source of funding for this work. Thank you all. I'd like time to answer questions.